Hi, I'm Dr. Jim Zoval, professor of chemistry at Saddleback College. You're about to watch one of my video lectures. If you like this lecture, you can get the entire Allied Health General Organic and Biochemistry course from the website address you see on the screen right now. Be sure to type the underscore between VOD and pages in this address. Enjoy the video. To understand these things we call significant figures, and we're talking about right now looking at a number and being able to tell by looking at it how many significant figures are in that number. Now if that's all there was to it, it would be just kind of a probably useless academic exercise. After I explain to you how to look at a number and know how many significant figures are in it, then you'll see why it's important when you do calculations. I'll explain that to you. First look at the number, see if the decimal point is present or absent. If it's present, then you go from the ocean to the land, kind of inspect the numbers going from the ocean to the land using this rule, starting from the left. That's why we have this decimal point present. You start from the left, go from the ocean to the land, just like evolution. Remember that? Good way to remember it. Then what you do is you count all the numbers, including 0, but you don't begin until you get to the first non-zero number. Then if your decimal point is absent, you just did it the opposite way, from the right to the left, doing the same thing, starting with the first non-zero number, count all numbers, including zeros after that. So we had an example, 0.00350. In this one, the decimal point is present, because there it is, and so we start this way, and you see, start with the first non-zero number. There's 1, 2, 3 significant figures. Then I gave you an example where the decimal point was absent, like this, 4,600. And we start decimal point absent, so we start from the ocean and go to the land. We started inspecting the number. Right, so there, no, 1, 2. And remember what this means. To a scientist, there is quite a difference in the precision between this number and this number. This number is only precise to the 100 spot. In other words, we know this number. We have no idea that and that. These are just there to keep that 6 in the 100 spot. If you didn't do that, it would be 46. Quite different number, right? So we put those zeros there, but we don't put a decimal point. When I put a decimal point, that means I was able to use whatever measuring device I was using to make this measurement. It was precise enough to tell me that those are actually zeros, not 1 or 3 or 5. Try a problem now. Specify the number of significant figures in each of the measured values below. Keep in mind, for scientific notation, only the number in front of the exponent matters in counting significant figures. Click pause and work on the problem. Check your answers. Notice in part B, the decimal point is present, so starting from the left, we don't start counting till we get to the 7, then count all numbers, including zeros after that, so there's 3 significant figures there. Try another problem. In this problem, I want you to write each of these measured values below in exponential or scientific notation. Be sure to give the correct number of significant figures. So if you start with 4 significant figures in standard notation, you should still have 4 significant figures when you write the number in scientific notation. Click pause and work on the problem. Check your answers. Note that you should have the same number of significant figures in scientific notation as you did in standard notation. For example, in part C, you started with 1 significant figure in standard notation, therefore you still have just 1 significant figure in scientific notation. Do that. Let's say you're going to do a calculation. And let's say you're going to calculate, I'm going to give you an example where you're going to calculate density. If you have a business and you're working in, say, people out mining minerals or bringing in rocks, gemstones, and asking you to calculate the density of these, how are you going to do it? Remember, does anyone remember the equation for density? You could just shout it out, but mass, density equals mass divided by volume. So if you were running this business, what would you do? You'd take the sample, you'd weigh it, and you'd measure its volume. Now, sometimes it's easy to measure volume if you have like a perfect cube. You do length times width times height. If you have a object that's not real symmetric like that, there's other methods to measure its volume, and you guys are actually going to do that in experiment 1. But you'll measure the mass and you'll measure the volume. And you'll do a calculation, you report a density. Well, you want to report the density to the correct precision. We're going to go into details of that, and I'll continue on this example. So when you're doing a calculation involving measured numbers, you have to use these rules. So you won't memorize these rules right away, but you will know these rules at some point here if you do the worksheets and homework. When doing multiplication or division, like this, here's division, with measured values, the answer should have the same number of significant figures as the measured value, whichever measured value in there, that has the least number of significant figures. That's a mouthful, right? Maybe you guys are starting to meet each other. You guys are going to start to find study groups. Has anyone started maybe studying with someone yet? Or maybe, okay. So tonight at about 2:30 a.m., call your study partner and say, what's the rule for significant figures in multiplication and division? Okay. And they'll say this.
No, I don't think they say that.
Oh, they should. If she has high enough expectations for her study partner, it will. It's like kids, right? No, she said she did. She raised her hand.
No, she might not
After that, yeah. Or yes, I bet someone else, I'll take you up on that. So it's kind of like parenting, right? The kids will come up to your expectation, aspire towards. If you have low expectations,
Okay.
if you have, there'll be a difference. Now, they won't always hit it right away, right? No. Here's the rule for doing addition and subtraction. Completely different rule. So whatever operation you're doing with measured values, you do either use this rule or this rule. Okay? And this has to do with, there's a little bit of math background behind this. Let's look at the rule first. And I'm not even going to read it because you won't remember it until we start actually doing it. You guys could take a second and read this. So you probably still read it and don't know what the heck it's talking about. This is the kind of things, I don't understand what I read, I forget what I hear, but I learn what I do. So we'll do some of these. When you are, let's say you're going in to do clinical work and you're getting numbers and you're going to do a publication, the way you treat this type of stuff is called error analysis. And when you report a number, you'll report a number with a confidence interval. The concentration of this ion in blood is some number plus or minus some other number. You guys may have seen that before. But that's kind of an advanced move. This is the first kind of like beginning move to start to get to how well we know a number. And this is the method we'll use in here. Let's do an example. So up top here, what I did is I just rewrote that rule. When doing multiplication or division, the measured value with measured values, and we'll assume we're always doing this with measured values on the homework, on the worksheets. Assume all the numbers you get are measured values, and of course they will be in the lab also. When doing multiplication or division with measured values, the answer should have the same number of significant figures as the measured value with the least number of significant figures. So let's apply that and see if it makes sense. So here's our object. This is back to a density problem. So someone brings you a material. Its mass is 5.324 grams. You measure that, so that's a measured value. You measure the volume. The volume is 7.9 milliliters. And now you need to report the density to that customer. So you'll use the definition of the density, like you guys told me. Density is the ratio of the mass to the volume. These were measured values. You'll put those in to the equation, and then what do? You bust out your calculator, right? You guys could go ahead and get your calculators and do this. And leave the number on the display in your calculators. So when you do that, you get some number, right? You get on your calculator something like that, yeah? Now, if you reported this number to the customer, they're going to either think, wow, they're really able to very precisely make these measurements, right? But or they might say, no way, that there's something wrong with this person. No way they can measure anything that accurately. We don't have balances that could weigh stuff that accurately. So You have to use this rule. When your calculator, when you put 5.324 and don't enter anything else, the calculator assumes that that's really 5.324000000, and depending on what calculator, many, many zeros. And when you enter 7.9, it thinks you're entering 7.900000000, so it does this. But we know that's not really the case. We have to be smarter than the calculator. We have to report this number only with numbers that we know. Think about it just overall. Does it make sense, since we only know this number to, about the 1/10th spot? We don't really have such precision here. Do we really think that we could know this number way out here? No, that's just an artifact of the calculator, thinking that those were pretty close to exact numbers that you put in there, but they're not exact numbers. They're measured values. We don't know our balance wasn't good enough to know what that number is or that number. And our volume measurement wasn't good enough for us to know these numbers. So now that's when we apply these rules. So let's see. When we're doing this calculation, right, the answer should have the same number of significant figures as the measured value with the least number of significant figures. How many significant figures are here in this number? And here? 2. So how many should I have in the answer? Right. Okay. So now what do? We do that round thing, right? We have to round it to 2 significant figures. So where would we round it? Well, the decimal point's present, so we're going to go this way. We don't count that 0. 1, 2. So either in your mind, or maybe when you're just starting on this on your piece of paper, draw a line right there. I'm going to throw these numbers away, but there's a round-off. Actually, there's many different ways in round-off systems. We're going to use the one that applies to these type of problems. What you do is you look at the first number you're going to throw away. These doesn't matter what those are. You look at that number. And if that number is 4, 3, 2, 1, or 0, if that number is less than 5, you just leave that 7 alone. If that number is 5 or greater, you round that up by one unit right there. Okay? In this case, it's 3, so we're going to leave it alone. So this is the number you report. And remember, we're never going to write a number without a unit. Well, I shouldn't say never. There's only a few exceptions in this class, and I'll let you know when that is. Grams per milliliter. That's a density unit. We do the math with the numbers to get this. We do the math with the units to get grams per milliliter. Let's do now an example for addition and subtraction. Now for addition and subtraction, it's a different rule, and that has to do with the math background of how this works. We're not going to go into those details. I'll kind of infer where that comes from in a bit. But I'm going to put the rule up there again. When doing addition or subtraction with measured values, the answer should have the same precision as the least precise measurement, least precise number used in the calculation. Notice it doesn't say anything about significant figures here. Different rule. For addition and subtraction, you use one rule. For multiplication and division, you use another rule. Let's say you measure the height of 3 objects, and then individually you measure the height of one object with a particular ruler. You measure the height of another object with, say, a different ruler with a different precision, and the height of a third object with even a different ruler. And then you stack those 3 objects together, and you want to know how high is the stack. You could either measure the whole stack, or you could just add the numbers that you already calculated, the height of each object. And this is an example of when you'd use the rule for addition and subtraction. So for this example, we're going to say we measured the height of a book, which was, with the ruler that we used for that, it was 50.85 millimeters. Then we measured the height of a box, and with the ruler we used for that, it was 168.3 millimeters. And then we measured a piece of paper, and we measured the thickness of the piece of paper, and we had some really good digital calipers, and we were able to do that. And now we made the stack, and we want to know how high the stack is. So what do? First, we put those numbers into our calculator. Remember, we used to add them up old school, just add the columns up, line up the decimal point. And when you do that on your calculator, you'll get this number. Now we have to apply this rule. The answer should have the same precision as the least precise measurement used in the calculation. Of these 3 measurements, which one is the least precise? The top, the middle, or the bottom? You see the middle. You see why? This one is precise. You look at how many places after the decimal point you have numbers. This one is precise here. This spot is the 10th. Right? This is the 1 spot. This was precise to the 10th of a millimeter to the 100th of a millimeter. This one is precise to 10th of a millimeter, 100th of a millimeter, 1000th of a millimeter. This one is only precise to the 10th of a millimeter. So that middle one is the least precise of all three. That's how you inspect them and see the precision. How far out does it go? This one is 10 times more precise than that, right? It's got that. This one is 100 times more precise than that. It's because we used a different device to measure it. So now, you see how we don't know this spot right here? We don't know what number goes right there. So does it make sense to you that we really wouldn't know what number goes right there? That's where this rule comes from. What you could do is you could draw a line, line them up either in your head or on a piece of paper and draw a line where your precision ends with that least precise one. And since I don't know this, I got to throw away that. If we apply that rule, we find this is the least precise. This one is precise to the 10th spot. So I could only make my answer precise to the 10th spot. So you're going to round to the 10th spot. Notice in this case, we look at that number. There's the first one we're going to throw away. It's greater than 5, so we're going to add 1 unit to this. We're going to round it up, we say, and we make that number 219.2 millimeters. So when do we do this? Add and subtract. And so we're going to do this in the homework and the worksheets and the labs. Resistance is futile. Just start doing it. How often? When are you going to stop doing this? Never. Right. Some people say, well, as soon as I'm out of your class. Now, remember we talked about being a professional? You're going to always do this. You want to drive your biology teachers crazy? It's kind of fun, right? Yeah, some of them don't, but yes. They still won't teach it. They put it on us, the chemistry teachers. You're going to be doing online homework, and sometimes you'll have multi-step problems like this times this times this, right? Don't do this times this, then round it, and then that number you get times the other one and round it. Do the whole thing. Do all the multiplication and then round it, or do all the addition and then use the significant figure rule. Okay? All right, try some. Here's the calculation. Pretend these are measured values and report the answer to the correct number of significant figures. Let's look at A. Any questions on A? Let's look at this one. 58, multiplication and division. So the answer should have the same number of significant figures as the measured value with the least number. So 2 significant figures, 4. So my answer is going to have 2. Good question came up. Do we write 58 or 58 point? Let's look at both of these. 58, decimal point absent, right? So we're going to go this way. 1, 2 significant figures. This one, decimal point present, how many significant figures? 2. So it really doesn't matter. Usually we don't do it. It's only when this last number here, it's only when there's zeros involved where it gets tricky. So usually we go like that. If you went like that on a test, that wouldn't matter to me. That'd be fine, equally correct. I'm just concerned about the number of significant figures.
What if the 12 had a decimal point after it?
If you had this times this, you mean? Well, we'll use the same rule. How many significant figures here? How many here? How many should the answer have? So, no, it doesn't change it. Okay.
I don't need to put a decimal point after the answer.
The 58?
Yeah.
You can't. You don't. But it only matters whether you put it or not if it changes the number of significant figures. When this number is not a 0, it doesn't. If that number was this, then it would matter, right? Because if I did that, it would just be 60, meaning I know it's probably somewhere between 55 and 65, right? If I put this, I know it's probably somewhere between 59 and 61, right? This I know 10 times more precisely than this. So it's only when there's zeros there that you have to think about, should I put that decimal point there or not? Okay? All right. This one, you all right on this, everyone? Usually I get some questions on that. Anyone want to see it done? Number one mistake people make is using the multiplication and division rule on addition and subtraction. Don't fall down that hole. Let's say first time you walk down the street, you're not looking and you fall in the hole. Second time you walk down it, you are looking, but you still fall in the hole. Third time you take a different street. So we do this, right, whether you do it by eye or whether you do it by the with your hopefully you get the same number. We're okay so far? Okay. Now, I'm not going to say, well, 4 significant figures, 2 significant figures, and round that to 2. That's the rule for multiplication division. The answer for addition and subtraction, the answer should have the same precision as the least precise number. So see, this is precise to the 100th spot. This is precise to the 1,000th spot. Or I could say, this is precise to 2 places after the decimal. This is precise to 3 places after the decimal. So can you guys see this is the least precise number? The answer should have the same precision as the least precise number. Precise to 2 numbers after the decimal point, to 2 numbers after the decimal point. Remember that thing we did where we draw that line where you run out of numbers? That's telling you the same thing. So I have to round it here. Less than 5, so I leave that alone and I say 5.00. Hi, I'm Dr. Jim Zoval. If you like this video and you'd like to get the entire course or just some of the chapters on video, I have the entire course and video lectures at the website you see on the screen right now. They're available on demand. The period of the rental is for a full year, so you'll have this video through the entire course. You could watch it as many times as you want, whenever you want. Happy studies.